Hi, this lesson is about one-to-one functions and inverse functions. So first let's talk about a one-to-one function. A one-to-one function is a function that for every element in the domain, there is only one unique element in the range. So if the values of y are repeated, then the function is not one-to-one. So an example of something that is not one-to-one would be y equals x squared, because when x is equal to 1, y is equal to 1, but when x is equal to negative 1, y is also equal to 1. So if you have any kind of repetition in your y values, that disqualifies it as a one-to-one function. So another way to identify a function as one-to-one is graphically. So a function can be identified as a one-to-one function by something called the horizontal line test. That is not the same as the vertical line test that we've talked about in previous lessons. With the horizontal line test, if any horizontal line intersects the graph in more than one point, then it is not a one-to-one function. So something like x cubed is a one-to-one function because if you can imagine having a horizontal line scanning through this graph at any point, it will only touch that graph once. So if it touches it twice, it would fail. So again, if I go back to the x squared function, the graph looks like this with a vertex at 0, 0. And as you can see, any horizontal line would touch this graph twice except at the vertex. So if it fails the horizontal line test even once, then it's not one-to-one, because again, that would mean that there are two y values available. So here, let's say this is a value of 4, the y value of 4 would appear twice on this graph. Okay, so why do we need to understand what a one-to-one function is? Well, that leads us to the concept of inverse functions, which we'll talk about in a second. Here's another example of something that's not one-to-one. Here, you touch this twice. All right, so a function that is one-to-one has something called an inverse function. An inverse function is a function that pretty much undoes the action of another function. So if you have two inverse functions, let's say f and g are both inverse functions, then f of g of x is just x. And again, if they're both inverse functions, then g of f of x would also give you x. So the taking the composite of two inverse functions just results in the input value of x as a final answer. So again, if f of g of x were inverse functions and I said evaluate f of g of -5, the answer would just be -5. You wouldn't have to do all the algebra to figure that out. And again, if f of g of x were both inverse functions and I said evaluate g of f of 12, well, you would say that's just equal to 12, right? But that's only if they're inverse functions. Another interesting attribute about inverse functions is that if you have two inverse functions, then the domain of f of x becomes the range of g of x, and vice versa, the range of f of x becomes the domain of g of x. So domain and range switch. So if xy is a point on f of x, then yx will be a point on g of x. So in other words, the x and y values flip, and that's because domain and range flip. So notation. If f of x is one-to-one, then this is what we call our inverse function. This is not f to the -1. This is read as the inverse function of f of x, or f inverse of x. So be careful with that. It's not an exponent. So the inverse function of x is not the reciprocal, the way we were using our rules for exponents. That is not true. So this just represents that it is the inverse function of f of x. So be careful with that notation. All linear functions of the form y equals mx plus b are inverse functions. Again, any linear function of that form is actually going to either be going upward or going downward from left to right, and that depends on what the slope is. And so that's definitely a one-to-one function. Again, any one-to-one function will have an inverse. Horizontal lines, like of the form y equals b, are not inverse functions. Again, that would fail the horizontal line test infinitely many times. So if I said this is the line y equals 3, there would be infinitely many points with the same value of 3. So that wouldn't have an inverse function. And neither would vertical lines, because vertical lines aren't even functions. Because for every one value of x, there's infinitely many y's. So this vertical lines, the form x equals a, that fails the vertical line test, so it's not even a function. And horizontal lines are functions, but they're not one-to-one functions. So neither vertical nor horizontal lines will have an inverse. All right, so here's an example of a linear equation. We want to show that f of x equal to 3x minus 1 and g of x equal to 1/3 x plus 1/3 are both inverse functions. And so in order to show that, we want to show that f of g of x is x, which is what I mentioned here. If you can show either one of those are equal to x, then you have proven that f and g are inverse functions. All right, so I'm going to do f of g of x, although g of f of x would also work. So that means g of x is the input into your f of x. It replaces the x. So that's what you see here. I have 3 times 1/3 x plus 1/3, and then there's the minus 1. You have to distribute the 3, which is what I did on this line. So you have 3 times 1/3 x plus 3 times 1/3. The 3's will cancel here in the first two terms. So you end up with x plus 1 minus 1. The 1 and the minus 1 cancel each other out, so you get x. And when you get that as a result, you can say that they are inverse functions. So how do you actually find an inverse function? So here I gave you what the two inverses are, but there's actual steps that you can follow to find out what the inverse function is. So as long as f of x is a one-to-one function, you'll be able to find f inverse or the inverse function. So first step is to replace f of x with y. So if it's stated as f of x equals some function of x, you change f of x to y. Then you flip the x's and y's. So the y becomes an x, and if you have more than one x on the other side, you change them all to y. Then you want to solve for y. And then how you solve it depends on what type of equation you have, whether it's linear or quadratic or radical or rational. You have to solve for y. And then once you get y alone on one side, you replace the y with that notation, f inverse of x, which means you have found the inverse function. There are times when the domain might have to be restricted on what f inverse is in order for it to remain as an inverse function. And so we'll look at an example of that later on. All right, so here we have another linear function. I have f of x equals 4x minus 4, and I want to find the inverse. So we're going to follow these 4 steps. So first I replace the f of x with y. Then I swap out the y becomes x and the x becomes y. That's what you see here on line 2. Then we have to solve for y. So first I added 5, and then I divide both sides by 4. So you get that y is 1/4 x plus 5/4. And then your final step is to let y be f inverse. So the inverse function is 1/4 x plus 5/4. Okay, so let's do another one. This is a rational function. You're given h of x is x over x plus 9. That is one-to-one. So if you were to graph it, you would see that it satisfies the horizontal line test, and we want to find its inverse, which we're going to call h inverse of x. All right, so step 1 is to replace h of x with y, which is what you see here. Then swap out the x's and y's. So the left side becomes x and the right side becomes y over y plus 9. Notice that both of the x's change to y. So if you have more than one x, they all change to y. Then we have to solve for y. So that creates a bit of trouble because you have y's in both the numerator and the denominator. So I need to be able to bring them together on the same line. So first thing I did was I cross multiplied. So the y plus 9 gets multiplied by the x. So you get x times y plus 9 equals y. Then I distributed. So I get xy plus 9x equals y. So now I have y's on both sides of the equation. You need to get them on the same side, and the 9x you need to get onto the other side. So in this next line, I subtracted this y over to the left, and I subtracted this 9x over to the right. So we get xy minus y equals negative 9x. Then, again, because I need to solve for y, you need to get just one y. I factored out the y from these two terms, and that leaves me with y times x minus 1, and then divide both sides by x minus 1 so that my y is alone on the left. So you get negative 9x over x minus 1, and then your final step is to replace y with h inverse. So h inverse of x is negative 9x over x minus 1. All right, so let's do another example with a radical, but we're going to go a little bit further. We're going to find the inverse. We're going to state the domain and range of the function and the inverse, and then finally graph these. So we want to find f inverse of x for f of x equal to the square root of x plus 1. So first step is to replace f of x with y. Next step is to swap out the x and the y. So the y becomes x, the x becomes y. Then I have a radical equation, and the way to get rid of this radical is to square both sides. So that's what you see on this line. The left side becomes x squared, and when I square this, the radical goes away, so you just get y plus 1 on the right side. Then you have to subtract 1 from both sides to get the y alone. So you get that y is x squared minus 1. And then last step is replace the y with f inverse. So f inverse of x is x squared minus 1. Okay, so notice that f inverse is not 1-to-1. If I were to graph that on its own, it's a parabola with a vertical shift 1 unit down. So it would look like this if I were to graph it on its own, definitely failing the horizontal line test. So that means there's going to be some sort of restriction on the domain. So let's talk about domain and range for f of x and f inverse. All right, so f of x is my radical. So I have square root of x plus 1. So again, if you remember shifting, this will take the square root function and shift it 1 unit to the left. So your domain is -1 to infinity, and your range is from 0 to infinity. And if you recall, domain and range flip when you find the inverse. So the domain becomes the range of f inverse, and the range becomes the domain. And if you keep that in mind, when we graph this, it will actually work out to be a graph that looks like two inverse functions. So I'm going to graph in part C, I'm going to graph f of x, and I'm doing that in blue, and that's the radical, and I'm going to graph f inverse in this purplish pink color. And that's your parabola, but remember, domain and range are restricted. So your radical is this blue line here. It is the square root function shifted 1 unit to the left. So it starts at -1, 0. But your domain for your parabola is from 0 to infinity. So instead of going all the way through the way we normally would, it's going to start at 0, -1, which also happens to be the vertex, and then it goes up to the right, only to the right. And your range is again from -1 to infinity. So remember, when you find inverses, the x's and y's flip. So here I have -1, 0, and so here I have 0, -1. The x becomes the y becomes the x, and that's true all throughout. And then another interesting thing about inverse functions is that when you graph them on the same grid, the way we did here, the line y equals x ends up being like a mirror image of the two graphs. So if you were to flip the function f of x over, it would become f inverse. So when I say over the line y equals x, so think of y equals x as a mirror, and it reflects the function and its inverse over to each other. And that'll be true for any graphs of inverse functions, not just this one. Okay, so that's the lesson. So give the homework a try. Good luck.